Okay, maybe. Okay. Okay, so now it works. Okay, thank you again. It's nice to come to GGI. Okay, today I'm going to talk about my recent work, like gauge origami and Quiver W-algebras. So based on several my recent works with Noshita Gokun, he's a PhD student in University of Tokyo. So we have two papers here. And okay, so what I'm going to talk about is okay, maybe so these terminologies are not so much familiar. So then let me start with a bit of motivation and introduction. So the first motivation is okay, so something called a BPS CFT correspondence. So I think this word was initially used by the Nekrasov, I think already 20 years ago. So the idea is that, okay, following. So this is a correspondence. So this BPS side, this is a BPS object in a supersymmetric gauge theory or string theory. And the CFT is a, okay, certain CFT-like theory. For example, in general, so this is a vertex operators or this kind of typically infinite dimensional algebraic structures. So more precisely, so for example, this BPS side, so we have a BPS object or BPS operators in a supersymmetric gauge theory and also string theory, M theory. And that corresponds to a certain operator, typically vertex operators. And okay, so this is a physics language, but mathematically, so this is this may be interpreted as a consequence of okay geometric representation theory. So mathematical point of view, so this BPS CFT correspondence may be interpreted as a consequence of a geometric representation theory. That means that, okay, so for example, this BPS side, gauge theory side, so we think about, for example, moduli space of instant or corresponding moduli space of BPS configuration, etc. So actually that gives you the nice, geometrically gives you the nice representation, that gives a geometric realization and representation of certain algebra, typically infinite dimensional. So that serves as some quantum algebra. So the mathematical point of view, so I think BPS CFT is almost replacement of geometric representation theory. So okay, then let me give you some certain canonical example. But I think the first canonical important example is that this AGT correspondence. And also, for example, the chiral algebras. So for example, this AGT correspondence is a correspondent, okay, equivalence, now equivalence between Nekrasov partition function on this supersymmetric side and the conformal block of certain quantum algebra, typical, for example, this Virasoro or W-algebra. And there are many extensions of this correspondence. So this is one of the most canonical example of this BPS CFT correspondence. And also chiral algebra, like the BPS, okay, typically so 460 SCFT, so we have a BPS sector, and then we can identify some chiral algebra, and then we can discuss what is the correspondence between central charges or levels of etc. Okay. So anyway, so then this way, so we have a main example of this BPS CFT correspondence. And then motivation today is basically the extension of this BPS CFT correspondence in a sense that is it possible to give it a more many and many example in this direction. So okay, so then I briefly mentioned about for example AGT is associated to the, for example, 4D n equal 2 supersymmetric. If you want this to the 5D n equal 1, I mean S1 compactification version, even you can think about the torus compactification of 60, still 8 Suji theory. And the chiral algebra, okay, so initially studied for the 2D, 4D n equal 2. And also we can extend the 60 n equal 2 comma 0 as well. But today's roughly the motivation is that some extension, okay, so then a high dimensional extension. So this is a higher dimensional extension is one of the motivation to study this gauge origami that I'm going to explain. Okay, so then let me briefly explain what is this gauge origami. So just one line. So this is basically the D0, D2, D4, D6, D8 system. Now let's think about C4. So okay, so basically this gauge origami is a D-brain system of a bunch of the D-brains in different dimensions. And okay, so then for the moment we think about the C4, but if you want, of course, you can think about more general setup. And of course, this system is frequently discussed in the context of gauge theory and string theory. But I want to emphasize that, okay, one of the property here is that, okay, so these are brains just a point, right? Okay. And then because this is a DR8 dimension, okay, this D8 plays a role of the kind of flavor brain wrapping a whole geometry. And then I want to emphasize that, okay, even this D2, D4, D6, so these are also, living on a non-compact plane, like just a C or C2 or C3. So this is slightly maybe different from the standard setup. For example, in the case of, for example, Gromov-Witten or something, we think about the similar D0, D2, D6, but now this 2 is now wrapping a compact 2-cycle Caravia, etc. But okay, ideas is similar, but the setup is now, everything is now living on a non-compact plane, basically. Okay, so then, for example, let me give you the certain example, and then I give you the flavor of this. Let me start with this standard case, D0, D4 system. And now, okay, so now we don't have a D6 nor D8, so then just D0, D4 plane is living on the complex 2 dimensions. And then in this case, okay, this gauge origami just gives rise to the standard H2G gauge theory. Depends on the notation, but for example, 4D n equal 2 or 5D n equal 1. And in this case, we can, okay, for example, this 4D n equal 2, or depend on the situation, but the 5D n equal 1 super-Ramirez theory. Okay. So in this case, so we know actually that we can write down a partition function of this theory, which is actually the Nekrasov partition function. Okay, some lambda. Okay, I don't write the explicit formula, but schematically, so this partition function is given as a summation over the lambda. Now lambda is partition. Partition is just a configuration of boxes. Yes. Okay, that's fine. And then next example, okay, so then, okay, before going to this, so now, for example, this D0, D4, and then D0 is point particle, and D4 is now living on, for example, C1. Okay, now we have 4 directions. For example, this D4 is now living on the first and the second complex plane. Okay, but in general, you can think about a more generalized situation like a D0, D4, extending in a 1, 2, and also D4, for example, extending in 2, 3, etc. So that we can add the D4 plane extending in different directions. And of course, in this case, we should be careful about, for example, supersymmetry condition. Like if you arbitrarily add D branes, of course, that may violate the supersymmetry. But of course, we need to care about this kind of argument. But anyway, so then after having D4 brane extended in different dimensions, so we can similarly write the partition function. But for example, this lambda is now, for example, associated with 1, 2 brane, 1, 2 direction, 2, 3 direction, etc. So then we can parameterize the partition function as a summation of the bunch of partitions. Each partition corresponding to the configuration in the 1, 2 direction or 2, 3 direction. Because, okay, so in order to write down the partition function, we have epsilon, for example, 1, epsilon 2. This is a so-called omega background parameter that plays a role of regulator of this partition, moduli space if you want. And actually, of course, this if you think about D4 brane extending in a 1-2 direction, okay, we have epsilon 1, 2. But if you think about, for example, 2, 3, so we should think about a similar contribution depending on epsilon 3, 2, and 3. Now we have in total C4, so it's natural to introduce a 4 omega background parameters. Okay, I will come back to this more later, but okay. Okay, then the next example is D0, D6 system. And okay, so then we can similarly have, okay, it's no space sufficient. So we can similarly have, okay this. Okay, the difference here is now this pi is plane partition. Plane partition. Plane partition is a 3D generalization of partition above. Okay, so it's a bit difficult to draw, but now this is a 3D partition here. So reason is clear because now we have a D6 plane extending, for example, C1, C2, C3. So then this actually each axis correspond to, for example, first complex plane, second, third. So that's why we have a 3-dimensional analog of partition, which is called a plane partition. And okay, so then, for example, this plane is studied in many contexts, like for example, in the DT invariant of 3-fold, for example. And for example, similar configuration is studied in the context of topological vertex or this kind of thing. Yes. But now, okay. Okay, so then, but now, so we have in total 4 epsilon parameters. And then, for example, compared to the Calabian 3-fold case, of course, for example, this we have epsilon 1, epsilon 2, epsilon 3 for D6 plane. So if you have a D6 plane on C1, C2, C3, we naturally have epsilon 1, 2, 3. But if you impose the Calabian condition, Calabian 3 condition, so then Calabian 3 condition means that epsilon 1, epsilon 2, epsilon 3 equal to 0. So this is a Calabian condition. And then in order to, for example, if you think about topological vertex, etc., so we typically impose this condition. Yes. But now situation is slightly different in the sense that originally this DC, okay, originally we have a C4. So then this D0, D6 is just a subspace of C4. So then we also have, okay, we also have epsilon 4 as well. So then the Calabian condition should be also promoted to this Calabian 4 condition. That means that, okay, sum of epsilon I to 4 equal to 0. Okay. So this is a slightly different in a sense. Okay, if you immediately realize D0, D6, it's natural to impose the Calabian 3 condition. But now we realize D0, D6 as a subspace of Calabian 4. Now we have one more parameter basically. So Calabian 3, we have 1, 2, 3 with one condition, effectively 2. Calabian 4, okay, we have epsilon 1, 2, 3, 4, but the one Calabian condition, then we effectively have 3 parameters. So then this, okay, in my sense, this D0, D6 is a bit one parameter deformation of standard, for example, topological vertex system or something like this. Calabian 4? Yeah, so yeah, so yeah, for example, yeah, it's a nice question. So for example, the D0, D2, we don't need such Calabian condition. For example, epsilon 1, 2 can be arbitrary. But 4-fold case, actually, so okay, I'm going to talk about a bit the mathematical side. So then maybe that can be. For example, okay, just one word. So this kind of partition function can be interpreted as a generative function of equivalent of Donaldson-Thomas invariant. For this purpose, Calabian condition is really essential. Otherwise, we cannot find DT invariant, etc. Yeah. So this is one of the example, one of the explanation. But we have several, of course. Of course, formally we can relax this condition, but all the computations are really complicated, and in many cases it doesn't work. Yeah. Okay. So okay, so this is 0, and then the next example is okay. So, and then I think it's better to mention that okay, so this kind of configuration is recently studied by I think the Pomoni Yang Cao Sang, which is called a tetrahedron instanton. Eri Pomoni Yang Sang. Yes. So this configuration is called a tetrahedron instanton. And then similarly, we can think about the D6 plane. Okay, now we have 1, 2, 3 direction, but we can also put the D6 plane on 2, 3, 4, or any combination out of 4. Yes. So this kind of configuration is now called a tetrahedron instanton. Okay. Then next example is D0, D8. And with technical point of view, so we should also add a D8 bar. But okay, so we can think about this kind of situation. And this configuration is now called magnificent 4 configuration. I think this is Nekrasov Nekrasov Piazzarunga. Sorry. Okay. And the mathematical counterpart is Yaron, Ku, and Monabari, etc. Okay, and what is a partition function looks like? How this partition function looks like? So this is a row 0, and now row is so-called a solid partition. So solid partition, okay. Solid partition is actually the 4-dimensional generalization of this partition. So then, unfortunately, I cannot draw, but this is actually the 4D partition. So I think it's really natural in the sense that because now D8 brane is now wrapping on a whole geometry C1, 2, 3, 4. So then corresponding, for example, combinatorial object is naturally uplift to the 4D analog of this. So then the 4D partition is now called a solid partition. Okay, and a bit technical remark, but in order to stabilize D0, D8 brane, so we should also add a anti-brane contribution, but it's a bit a technical point anyway. Okay. So then, okay, so we can think about many combinations. And then let me give you our result, the proposition. Is a foreign. So we have partition function. Okay, so then in general, so we can compute a partition function of gauge origami using standard supersymmetry localization, etc. So for example, we have for example k instanton sector. Okay, now k is a number of diesel branes. D0. Then okay, so initially, so this first of all, this k instanton sector or k diesel brane sector or partition function is given by equivalent integral over the corresponding moduli space. For example, in the case of diesel D4, this moduli space is nothing but the k instanton moduli space. And then, for example, diesel D6, so we similarly have a notion of moduli space, but in this case, mathematically, this moduli space is identified with a corresponding moduli space of a coherent shift of over C4, C3, etc. And in this case, okay, so this meaning of integral should be very careful. For example, virtual dimension is going to be 0, so we should instead think about the virtual fundamental class, etc. So we need a bit technical complication, but anyway, already this k instanton partition function is given by integral over the moduli space. That typically computes the volume of this moduli space in a regularized sense. Okay. And then, okay, this partition function has a natural, typically we have a so-called K-theory uplift of this integral, okay, this. And then, okay, we have several conventions, but I'm going to use a Todd of, okay, Todd class insertion. Okay, so in the language of this D0, D4, this is a 4D partition function, and this is a 5D partition function, 5D theory compactify on S1. So in this case, instead of integral of just 1, so we instead think about the Todd class. Or if you think about, okay, if you apply a bit different notation, so this Todd class can be replaced with a roof class or something like this. But anyway, so this computes some index. Okay, so this is more or less the definition of partition function, and then the claim here is following. So we have, okay, so d phi. So this is actually our BPS correspondence for this gauge origami setup, in a sense that, so this partition function has an expression in terms of the correlation function of certain vertex operators. And then, so interpretation is that now A operator plays a role of this D0 brane vertex operators. And this choice of B is actually certain, okay, so this is a vertex operator of, okay, this is several possibility. Depends on what kind of theory you are talking about. D4, D2, 3, 6, D8. Vertex operators. Okay, so then the claim is following. So this is a more or less geometrically computed, I mean, starting from the gauge theory computation or equivalent localization. And our claim here is here. So partition function computed using a localization can be written as a correlation function of certain vertex operators. For example, okay, this -1 is a bit convention, but the A is this serves as a D0 brane correlation operator, say vertex operator. And the V, this depends on theory. If you think about D0, D4, so this V should be, we should think about some certain vertex operator corresponding to D4. If you want to think about, for example, D0, D8, we should think about the vertex operator corresponding to D8. So in that sense, this part is actually, this part depends on what kind of theory you are talking about. But for example, this part is actually this D0 brane contribution is nicely organized by here. And then now we have, for example, integral over this phi. So this is, okay, physically, now we are thinking of some dynamics of dynamical system of this D0 brane, in a sense that, for example, now in this case, each box roughly characterizes the position of the D0 branes, in a sense that now, for example, we should think about all the summation over this configuration. That means that we should take into account all the possible configuration of D0 branes. So that is a more or less path integral over for this D0 brane degree of freedom. And this integral over phi means that this is basically corresponding integral over the position of D0 brane, etc. And this B part plays a role of more or less framing or flavor degrees of freedom, if you want. Okay. Okay, more precisely speaking, so we can also think about some integral of some, for example, these. We can also think about the integral over the position of, for example, D2 brane, etc. But this is, okay, I will briefly mention the generalized version of this story. Okay. Yes, this is 8-dimensional theory. This is still analog of the instanton, yes. Or otherwise, okay, for example, mathematically, so this partition function computes the equivalent volume Hilbert scheme of points on C4. So then points correspond to D0 brane. Okay, yes? Yes? Okay, so this part, at this moment, so no dependence partition. And for example, this position of, for example, D4 brane is going to be identified as a Coulomb branch parameter in a gauge cell context. So then, but in this context, for example, recording D0, D4 case, defined on as C1, C2, Coulomb modular is a kind of just parameter. We don't integrate up this. So then that plays a role of kind of flavor. Okay, of course, we have some position of these vertex operators. This is going to be identified with a position of branes, depending on the context, but plays a role of Coulomb moduli. Integration variable means that now this phi, this part only depends on phi, only depends on x position of flavors brand, and then we have non-trivial OP-like objects. So then that gives you the, for example, interesting combinatorial partition function like necklace of function or something like this. And yes. Okay, so in this D0, D4, this is a, okay, many ranges, but the cohomology or K-theory, equivalent K-theory. Physically, for example, 4D theory or 5D theory and something like that. So this kind of uplift is always possible. So yeah, sure, yes, yeah. Maybe I can talk about this. These are these as well, yes. Okay. Yes. Yeah. So that I'm going to talk next. Yes. That is actually the motivation of my talk, and then this is actually the motivation why I'm having a Quiver W-algebra in the title. So this is motivated by this thing. Okay, so at this moment, so the structure of representation, etc., is not yet clear, but more or less, I think it's clear in how to have such kind of a combinatorial picture. For example, this partition is going to be identified with some module structure of a fork module of corresponding algebra, like a quantum toroidal or this kind of Alpha-Yangian. And for example, this case, 3D version is similarly the quantum toroidal or Alpha-Yangian, but the representation is now called a magmaphone module or something. And okay, honestly speaking, D0, D8, solid partition, that in this case, not yet, interpretation is not yet established. But for example, construction of this vertex operator, etc., is really motivated by this or geometry representation theory or W-algebra or corresponding vertex operator algebras. Any other questions? Okay. So then rest of time I'm going to explain or more or less physically derive this correspondence and what is these vertex operators, etc., and how you can get these vertex operators. And Okay, so then as I said, this the concept of this BPS-CFT correspondence is really mathematical counterpart is basically geometry representation theory. So then, in other words, for example, looking at this equivalence, so this left-hand side is a partition function of certain BPS configuration that can be computed really from a geometric point of view, in the sense that we have a modular space of this BPS configuration. And if you think about the equivalent integral, you can get partition function. And the right-hand side is a really rather algebraic in the sense that, once you construct a certain nice vertex operator, which plays a role of creation and annihilation operators or vertex D-branes, so then you can immediately compute partition function. So that means that, that implies that, this is, right-hand side is more algebraic side, and this is a more geometric side. And the question is that, so how to convert geometric data into algebraic data? So this is basically the key part. So that is Otherwise, so this how to construct A or B from as a geometric data or configuration of this the branes living on the C4 in total. So then So then I'm going to briefly explain how to convert this geometry, how to convert the geometry to algebra. Okay. So this is a key step to construct the vertex operators. And Okay, so then so then let me first discuss the more more established example like Nakajima correspondence. So this is a more established version in a sense that, for example, we can, for the moment we think about the C2. And then if you think about the quotient by a certain discrete subgroup of SU2, so we can discuss, for example, OV4 or etc. And then now this is gamma is SU2 subgroup, discrete one. And this Makai-Nakajima correspondence, Makai correspondence is that once you have such singularity, so we can figure out some certain algebraic data. I'm now denoting like this, gamma hat, which is actually the quiver associated to this choice of this gamma, but affine version here. For example, I think it's better to give a certain example. So for example, if you think about gamma equal to the Z R, so this is R, C, R. So this cyclic group. So then the corresponding gamma hat is a quiver structure like R minus 1 hat. Okay, if you want to, this ZR type singularity is called A type singularity. Then maybe I abuse the notations, but now from this kind of geometric situation, we can get certain quiver structure in the end. Okay, so this is a most typical situation. And then on this side, we have a nice classification, which is called AD classification. So then this is A type is a cyclic group, and D type, dihedral, and then E type, etc. So every time, so we have a corresponding quiver structure. And then, let me give you the one more example, which is a R equal 1 case. Okay. So this is also, it looks like very trivial, but this is also important in a sense that, if you think about R equal 1, just identity, this quotient is really trivial, but still we have R equal 1 means quiver side is A0 hat quiver. What it is? So then A0 hat quiver is, quiver, something like this. So that is a very, it looks like trivial, but now this quiver has only affine node, that's it. But this is a cyclic quiver, so then we have loop. And then this kind of quiver is often discussed in the context, many contexts. And then this is called like, for example, Jordan quiver or something like this. And then actually, Jordan quiver is used to discuss modular space of instanton, which is really the ADHM. That is the reason why this is also called ADHM quiver. And then, for example, in order to discuss modular space associated to D0, D4, actually we should use this kind of quiver. So it looks like a trivial, but even this quiver structure is more or less non-trivial. Okay. And the next step is that, now that's fine. And then next step is that, so now we have some quiver structures. And then in order to more explicitly construct, vertex operators, so so we have one more step. That is, so Cartan matrix. Okay, so say quiver, Cartan matrix. So now, given such quiver, so we can construct a Cartan matrix. So this is a standard. For example, this kind of process is of course very established for the in the case of finite dimensional simple algebra, given Dinkin diagram, which can be identified with the quiver. So then we have a one-to-one correspondence to the Cartan matrix. And then so let me so my notation is that now gamma. Sorry, bit different notation, but I'm using this kind of notation like this. So this gamma is a quiver. Yes, this is a set of the nodes. This is a set of the edges. So then a quiver Cartan matrix is defined like this. So this Ij matrix element of this quiver Cartan matrix is given by 2 times ij minus h associated to 1 minus 1 j to I here. Then now ij is an element of gamma 0. And then this E is an element of gamma 1. Okay. So let us define this matrix. And okay, so let me give you the one comment about the notation in a sense that we have edge like I to j and j to I. But we now think about, okay, so in general, of course, we can think about the quiver like this, for example. And edges now, edges are oriented. But now we think about the so-called doubled quiver in a sense that in order to, in addition to original quiver, we also add edges in a different, opposite orientation here. So then from this point, all the edges are doubled. So then, for example, this if you have ij, we always have ji as well. Okay. So this is a current notation. So then initially this quiver can be, oriented, but now this is unoriented version. Then that can be identified with, for example, thinking diagram, for example. Okay. So then, for example, in this case, with this definition, what is a character matrix of this Ether hat? So this is actually Ether hat quiver is here, only one node. So then we have 2. This is actually 1 by 1 matrix. 2 minus actually 1 minus 1, which is 0. So of course this looks really trivial. Okay. But of course this is of course true in a sense that usually so this affine quiver or affine character matrix of affine thinking diagram. So that is okay. More or less the definition is that this corresponding character matrix has only one 0 eigenvalue. So then in this case we only have one node. So then the character matrix should be just 1 by 1 matrix. 1 by 1 matrix you should have and with a 0 eigenvalue. That only choice is just 0, real trivial. Okay, and of course in this case, okay, so as I said, okay, I said okay, this even we have a bit non-trivial structure, but the character matrix really trivial. So then in that sense, we need a bit of modification of this character matrix. So then let us think about this Q character matrix. With the deformation of character matrix. So we think about Q1, Q2, C-star variable, and also mu is also C-star variable for each one. Definition is here. So ij is 1 plus r. Okay, so let me use my notation. Q1, 2 is a product of Q1 and Q2. Okay, let's define a bit modification of this character matrix. Okay, it's going to be clarified, but for example, okay, so this Q1, Q2 is going to be identified with equivalent parameters of corresponding, for example, C1, C2. Otherwise, correspondence is that, for example, Qi is exponential epsilon I. So this is a multiplicative version of equivalent parameters. And actually mu e as well. So this mu e is going to be identified with a bifundamental mass for corresponding bifundamental, in this case, hypermultiplet, because now we have oriented edges, these are corresponding to the chiral, but now we have going and coming, going back. So then this gives you the hypermultiplet. Okay, so this is a definition. And then in this case, what is Ether hat? In this case, okay, 1 plus Q1, Q2 minus certain mu, and then the mu inverse and the Q1, 2. Now this mu is a parameter associated to this edge of this Ether hat here. Okay, so then looking this expression, actually we can realize that this can be factorized this way. plus Q1 to here. Okay, so from this point of view, if you put, of course, it's clear that if you put mu equal 1, so this character matrix is going to be trivialized, become 0. Same thing happen for this this choice. And okay, so actually, so this Quiver diagram is corresponding to the from gauge theory point of view. So this gives you the 4D n equal 2 star theory. I mean gauge theory. I mean having a vector multiplet and also adjoint hyper. So then mu equal 1 limit is corresponding to the adjoint mass less limit. That is the point where the supersymmetry is enhanced to n equal 4. So this is a special point of this story. And then let us, okay, so then from this point of view, let us define 1 minus Q. Okay, for the moment, let's think about, let's introduce the notation. Let's call mu Q3 and this part Q4. And actually, so this, okay, so then the motivation is that then, so we have, for example, Q1, Q2, Q3, Q4 is going to be 1. So this is corresponding to the epsilon 1, 4, it's going to be 0. Yeah, if you want, for example, how to engineer in this Quiver gauge theory in the context of, for example, C4 plane. So just put a D4 plane. Of course, the corresponding gauge theory is n equal 4, 16 supercharged gauge theory. But okay, so then if you insert flux in a transversal direction, this supersymmetry, I mean, R symmetry is violated to the SU2. So then this, actually in this context, so this flux plays a role of this adjoint mass. So then actually this Q3 is now interpreted as a flux along this transversal direction. And this is, again, then this is a motivation why we now interpret it as this mass parameter, adjoint mass parameter as a equivalent parameter or omega background parameter associated to the transversal direction. Okay. So then, okay, so then let me remark that actually this kind of factorization is really specific to this affine quiver, especially A-type case. And of course, we can similarly think about Q character matrix of, for example, finite A-type or B-type, etc. But we don't have such a nice factorization. This kind of factorization is really specific to the affine A-type case. Sorry? This one? Okay. Q1, Q2, Q3 is now mu. This is a definition. Mu inverse. Sorry. Mu inverse. Sorry. Sorry. Sorry, maybe something is wrong. Okay, so let me use, I think another notation is minus, and this is my favorite notation, plus and minus, then minus, and then a plus 1 and a minus 1. Then at this moment, I think that's fine. Yes, then the definition is here. Then minus 1 plus 1 Q1 2 inverse is going to be 1. Q1 2 is a product of Q1 Q2, so I think that's fine. Yeah, sorry for question. Okay, so then motivated this kind of observation, and let us give you the construction of these vertex operators. Okay, so then using this, okay, then let us introduce the D0 brane vertex operators. That is, I'm going to use this notation, this phi of x, a of x. This is exponential of n, a n x minus n This now, this is so-called free field realization of a vertex operator. So now this small a is operator, basically Heisenberg oscillators. Of course, we have a non-trivial coefficient, but just a linear combination of standard Heisenberg oscillators. And then, okay, more precisely, so we need a certain additional contribution, which is called a zero mode, etc. And then this dot means so-called a normal ordering. Okay, and the motivation here is the following. So now this diesel brain is now probing this C4 geometry. And then, okay, so compared to this, in this case, okay, I didn't discuss full details, but now this Quiver character matrix of this Azer hat type, this actually probes the C2, okay, C3 cross C4 out of C4. So then that is the reason why, so actually we have a Q3, Q4 dependence in this structure. So then, okay, having this kind of observation, so we can construct a diesel brain, now probing whole C4 brain, C4 geometry. And from this point of view, this diesel brain is really point-like. In that sense, it's natural to have a symmetry among whole Q1, 2, 3, 4. And then, okay, and actually, so this kind of vertex operator was initially constructed in the context of Quiver W-algebra associated to this Azer hat. Okay. Sorry, which? N? So you mean yes. So then your question, is it possible to remove the N dependence? Yeah, that's possible. Yeah, of course, that's possible. If you introduce just this part, and then in front of this, you can put some coefficient. But okay, I'm going to explain another D brain cases. So then this expression is more convenient to discuss other D brains. Okay. And then this, okay, just a remark is that this vertex operator was initially discussed in the context of this Quiver W-algebra associated with this Azer hat Quiver. Okay. So then let us discuss this D2 brain, this vertex operator. So now D2 brain is living on either C1, okay, 1, 2, 3, 4 direction. So then we have 4 possibilities. And let's think about S sigma of X, similarly exponential of S sigma n x2 minus n. Now sigma is now 1, 2, 3, 4, one of them. Then where S sigma of n is actually constructed from 1 minus q sigma of minus n. So this is just a rescaling of this original D0 brain oscillator here. So okay, we have several interpretations, but of course, depending on the q sigma is larger than or less than 1. But for example, we formally have an expression like this, q sigma of minus n, m equals 0 to infinity. Okay, this expression is available only when q sigma is larger than 1. But this expression, this interpretation is the following. So initially, in order to construct a D2 brain, so we can make it using infinitely many diesel brains. So this and the opposite direction is something called a tachyon condensation. So basically, we can construct a higher dimensional D brain starting from the lower dimensional ones. And now this is actually initially we have the diesel brain, which is a point right, and then put in a diesel brain slightly shifted in this sigma direction, for example, 1 direction. So then you can make in the end a D2 brain extending in the, for example, sigma 1 direction or 2 direction or something like this. Yes. So then in order to see this kind of picture, so I'm now using this notation. And we can similarly think about, for example, the D4. So then, okay, I don't explain for details, but for example, we can think about X specifically the 1, 2 direction, complex 1, complex 2 direction. So we have a similar exponential of then now this x1 to n is given by a n of 1 minus q1 minus 1 minus q2 minus 1. Sorry, it's a bit difficult to see, but anyway, so then the idea is similar in a sense that, sorry, n m l a n q1 minus, sorry, m n q2 minus L n. Sorry, maybe I missed something. So this n, sorry, n as well. Sorry. So anyway, so the idea is very similar in a sense that in order to make D4 brane vertex operator, starting from D0, but summing over the, one direction infinite sum and the second direction infinite sum to make D4 brane, actually. Okay. So then same construction holds for D6 and D8. Okay, so then let me demonstrate after using these vertex operators, what kind of partition function you can get from this correlation function of these vertex operators. Okay, for example, there's certain examples. So the first is this D0, D4. In this case, okay, so let's think about the zk as, okay, we have a k factorial of this. Product of a minus 1. Okay, this minus 1 is just a convention. And then we think about alpha equal 1, 2, for example, n of x1, 2 of a alpha, for example. So now we have k d0 and n d4. So that gives you the SUN k instanton partition function. Okay, so using this free field realization, actually computation is really straightforward, just using this Baker-Campbell Hausdorff form, compute this correlation function. Then, okay, let me just give you the, okay, it's a bit long expression, but okay, so let me introduce several notation. 1, 2, 2, 3, 3, 1 of phi ij. Sorry, k? Now we are talking about a k instanton sector partition function. K is fixed, and the n is now, okay, now we are thinking of n d4 branes.
Is this inside of the D8 break?
In this case, no d8, only d0, d4. So then that should agree with standard Necklace partition function, actually. And then, okay, so then notation is, yeah, in this case, we should add, for example, D8 brane vertex operator, etc. In this case, we similarly have a expression that agrees with some supersymmetry localization computation instead. Okay, and the phi ij is okay. So sorry. In this case, maybe we add some two. Sorry. So this is known to be the LMNS formula for this K instanton and UN theory used by a miss with an adjoint. So this bracket symbol means that, okay, basically this is a platistic exponential. This phi ij is just some interaction here. And then the notation here, for example, Q1, 2, 3 means that we have 3 factors, Q1 phi ij times Q2 phi ij, something like this. So it's a bit lengthy expression, so sorry for this. But anyway, so then using this correlation function, so we can nicely reproduce this LMNS formula, which is really counter-integral formula of K instanton sector of this partition function. And then, okay, now this should be interpreted as a counter-integral. So then all the computation should be understood as a JK residue. Okay, so then let me give you one more example to finish. Okay, so we have several, okay. So if you want, you can do the same thing for D0, D8, etc. But another example is that, okay, let me think about D2, D8 bar system. So this is a bit different type of the situation. But for example, we can think about the following. So then again, K, N. So now this, okay, this is a pair of D8, D8 bar. So then N D8 and then also N D8 bar. So then now this similarly have, okay, so let me use a bit of simplified notation like this. And then, for example, okay, let me explain the notation. And now this, okay, now this D4 brane is extending in, I mean, fourth direction. That's why I'm now having a Q4. And this is a so-called Q-shifted factorial or hammer symbol. And then now this A is basically the position of, A plays a role of basically the D8 brane position. And this K, A is now identified with the anti-brane position. So in this context, this K plays a role of actually detects the difference between D8 and D8 bar. So from this point of view, if you put K equal 1, okay, this becomes just 1. So that corresponds to just a pair annihilation of D8, D8 bar. And okay, physically, and precisely speaking, actually we should, okay, just using this formula. So then we have additional contribution, boundary contribution. Because physically this theory computes some singular partition function of certain gauge theory. In this case, we should be careful about the choice of boundary condition. And then actually boundary condition can be automatically reproduced from the OP of these vertex operators. And then the boundary condition is nicely interpreted as a stable envelope of, associated to this Hilbert scheme of points or C4, C3. But this is not yet complete. Almost this can be identified as stable envelope for Hilbert scheme of C2 or a higher rank version, which is a Kotte scheme of corresponding geometry. But almost stable envelope this Hilbert scheme, but not yet complete. So this is not yet understood completely. But looking at the formula, it looks almost same as a stable envelope of Hilbert scheme or C2 or C3. And so then another word is that this mathematically this partition function computes the is similarly the corresponding modular space is actually the Kresai map of P1 to actually this Hilbert scheme of this K. Yes, C2 or 3. Phi is phi gauge theory language. This is a Cartan of UK gauge theory. Yes. And yes. So yes. And then now this now we have an equivalent parameter associated with P1. So now this is like a Q4 is actually identified with the equivalent parameter or rotation parameter with P1 in this case. And then another interpretation mathematically is that this partition function actually computes the PT invariant of C3 or actually the C4, but a special case. So actually this Kresai map is identified with the so-called vertex function in the language of Okounkov. And then in the case of, for example, Quiver variety associated to affine Quiver, actually that computes corresponding PT invariant. This is Pandel-Pandel-Thomas invariant, which is a cousin of Donaldson-Thomas invariant. So actually, so we can use this kind of technique to to compute enumerator invariants like this. And then if you want, we can think about a more generic situation. For example, today I talked just only for C4, but if you want, we can think about a more generic toric Calabi-Yau fourfold. And then in this case, of course, we should think about some gluing, etc. And also we should modify a bit this algebraic structure. But basically, how to construct this kind of geometry is almost straightforward. Anyway, so this C4 is a really building block of all the toric geometries. So then we can make all the geometry out of this building block, like a C3 or C4. Okay, so I think time is now over. So let me stop. Thank you for your attention. In this case, partition function of D2, D8, and omega background is 1, 2, 3, 4. On C4, yes. Fourth direction is now base of this Kresai map. And then, for example, this if you think of, so then C4, now we have epsilon, somehow parameter Q4. And then depending on the choice, but if you think about the Hilbert schema C3, so now we have Q1, 2, 3 are identified with the equivalent parameter associated to this C3. So then in total, we have Calabi-Yau 4. This one? So this is, this is now K-theory set language. So then this is a C4. So sorry, C4 means a C4 cross, so C4 cross S1. Yes, that's true. Yes.
And then from when you describe it as a correlator, vertex operator, it is a correlator of what?
Yeah, so this is now a correlation function of D2 brane associated to 4 direction, phi, now K. And also we have a Z operator associated to, now this is, I think it's better to use a notation like this, Z of A and then a Z of KA. So this Z is a vertex operator associated D8, but we have a several geometrical discussion. Like we need a pair of D8 bar. So that's why we have, okay, this is a D8, this is a D8 bar.
But what do you mean by correlated vertex operator? Just back on that?
Now this is a correlation function with, in the sense of this Heisenberg oscillator.
In the vacuum one?
Yeah, vacuum, yes, yes. If you think about, okay, this is a vacuum expectation value, but of course you can think about other correlator like a character. In that case, this C1 is replaced with the elliptic curve. Okay, sorry, I couldn't have a time sufficiently, but for example, this construction is actually motivated by this W-algebra. Yes, yes, that I couldn't talk details, but yes. For example, this construction of this operator, for example, here, this diesel brain was initially constructed in the context of the W-algebra associated with Jordan Quiver. And now this okay, so this is purely more okay. When this was discussed, actually there was not yet geometric interpretation like a diesel brain creation operator, etc. But now, so we have a interpretation as a creation operator of diesel brain. Yeah, so this S is a screening current. Yes. Yes. Yes, precisely speaking, yeah, we should take care of some additional zero mode, etc. Yeah, for example, in order to match the precise, for example, the gauge theory computation, so we need a slight modification using zero mode, etc. But we can explicitly construct, okay, this zero mode explicitly to match the gauge theory result. Yes. Sorry. D0, D8 pair of Quiver means okay, yes, okay. This is another story, but for example, what I explained here is that only about 3-4 direction, because initially this was coming from, for example, discussion like this. But if you want, you can think about C4 is a, okay, so for example, thinking of C2 mod 1-2 direction quotient, and then a C2 of 3-4 direction quotient. So then actually, so we can think about Makai-Nakajima correspondence with respect to first 1-2 direction and the 3-4 direction. And actually, this combination of 1, 2, 3, 4, if you want, 3, 4 is nicely interpreted, directly interpreted this one. And if you think about the quotient with respect to this first one direction, actually we can also change the 1-2 dependence. So this, if you split 4 equals to 2 plus 2, we have a Quiver structure with respect to 1-2 direction and 3-4 direction. But of course, C4, we have another possibility of quotient or mixing all together. In this case, we have a bit more complicated thing, but yeah, we still have a similar Quiver structure in some special cases. Yeah, not generic, but yeah. Yes. Okay, so this case, this is related to this expression. For example, with respect to this expression, now assumption is Q, for example, in this case, Q4 is bigger than 1. Otherwise, this infinite product doesn't make sense, and this infinite sum as well. So now Q1, 2 is now supposed to be larger than 1. But if you want, yeah, of course, here. Okay, so this itself is okay. And for example, this, yes, in the actual computation, so for example, in thinking of this kind of correlator, when you compute each OPE, we should impose that, for example, this variable is smaller than this, etc. So we should be careful about this. But okay, so okay, I couldn't mention that, but of course we can always think about analytic continuation. And actually that really corresponds to the word crossing in this context. And then if you change the ordering, actually boundary condition jumps. And then this is really compatible with the discussion of stable envelope. Choice of radial ordering of these parameters. If you change this corresponds to the word crossing in this context. And then, yes, so in this case, we have boundary contribution. And this is actually same argument of how to get this stable, how to understand the stable envelope in this gauge theory language. Yeah, sure. Yeah. Mm-hmm. Yes. Okay, so okay, so this proportion is of course proved for, okay, not yet proved for generic case. And for example, that the D0, D4 case, for example, we can okay, we can get this counter integral formula, but this actually agree with the so-called Rose-Neclas-Château-Sibyl formula, which is a counter integral formula for this k instant on Neclas approaching function. And the similar expression is available for example, tetrahedron like a D0, D6 as well, and the D0, D8 as well. So then, for example, in these cases, so we can reproduce the counter integral formula computed from the gauge theory side. And for example, D2, D8 case, yeah, this case as well, there's some computation from the geometric side. So then we can see the agreement with this. So then, okay, so from this point of view, okay, it's not yet established completely, but at least norm result, we can reproduce this kind of norm result. Okay, in this case, okay, depends on the situation, but yes, so now we have Q1, 2, 3, 1, 2, 3, 4 with one Calabi-Yau condition. Now we have 3 parameters. And also, okay, if you especially think about the D8 brane, so if you think about D8 brane, we should always think about the D8 bar. So then we should also import this K parameter. So then in the context of, for example, affine Yangian, so this K plays a role of a central charge of affine Yangian or quantum toroidal. And then, yes, so then we always have 1, 2, 3, 4 is automatically fixed by the Calabi-Yau. And if you think about D8, we also have this K parameter as well. It's not a stable configuration. Yeah. There are several discussions of how to stabilize D0, D8. Yeah. C3 case, okay, so it also depends on several situations, but for example, I mentioned the so-called tetrahedron case. So this is a C3, Q1, 2, 3, okay, D0, D6, but within a C4. So then we still have a Q1, 2, 3. Yes. So then this is a bit one parameter more compared to, I think, affine Yangian or quantum toroidal setup. So that is the reason why this D0, D6 brane computes a bit the deformation of topological vertex like Parchon function. Thank you very much.